The fastest object humanity has ever built is moving at 190,000 miles per hour right now. And at that speed, the nearest star is still 70,000 years away. Not 70, not 700, 70,000. Entire civilizations could rise, collapse, and vanish before a human being traveling on our fastest machine ever made would even arrive. The galaxy itself is 100,000 light years across, a scale so large the human brain almost refuses to process it. Our Voyager probes, launched nearly 50 years ago, are already farther from Earth than anything we have ever touched. And yet they have not reached the nearest star. They are not even close. And unless something changes, they never will. Which raises a deeply uncomfortable possibility. Maybe the universe was not built for creatures like us to explore it. Maybe the stars are not destinations at all, just light suspended forever beyond our reach. A cosmic horizon line we can look at, but never cross. Or maybe there is another possibility, because hidden inside Einstein's equations, buried under a century of assumptions, physics quietly left behind something strange. A loophole, a crack in the wall, a way to move without technically moving faster than light at all. And for decades it sounded like pure science fiction, until researchers started taking it seriously, until papers started being funded, until a NASA lab reported detecting something they absolutely did not expect to see. If you are new here, welcome to Cosmio. Hit subscribe, pour something warm, and get comfortable, because tonight we are going to walk through how faster than light travel migrated from science fiction into a funded research frontier, why moving space itself sidesteps Einstein's speed limit, and what a 2021 NASA lab actually detected. Now, settle in and let's ease into this one slowly, because the numbers are going to get uncomfortable before they get interesting. The problem is not that humanity lacks powerful engines. The problem is that the universe itself seems fundamentally hostile to travel. Every breakthrough in transportation throughout history made the world smaller. Horses became ships, ships became trains, trains became rockets. But eventually space stops rewarding speed altogether. You can keep building faster engines forever and the stars still barely get closer. At some point, you run into a wall that appears absolute. Because according to Einstein's relativity, the speed of light is not simply a recommendation. It is woven into the structure of reality itself. The faster an object moves, the more energy it requires, until approaching light speed demands essentially infinite energy. The universe has a built-in speed limit, and nothing with mass is supposed to cross it. For most of the 20th century, that seemed to end the conversation right there. Faster than light travel belonged to science fiction alongside wormholes, hyperspace, and warp drives. Interesting ideas, great for movies, completely impossible in the real universe. But then physicists noticed something strange. Einstein's equations never actually said space itself could not move faster than light. And that tiny distinction changes everything. We have a concrete example of just how defeating the scale really is. In 1977, NASA launched the Voyager probes. They have been flying continuously ever since for nearly 5 decades, pushed along by gravity assists and their original momentum. They are the most distant human-made objects in existence, and they are roughly 14 billion miles from Earth. That sounds enormous. It is enormous by any measure that makes sense on this planet, but 14 billion miles is not even a rounding error on the journey to the nearest star, which sits about 25 trillion miles away. Voyager will never reach it. In roughly 40,000 years, Voyager 1 will pass within 1.6 light years of a star, called Gliese 445. Pass within. Not stop at, not orbit. Drift past. Silently, with no one left to receive any signal it might send. So the scale problem is real. But here is the question underneath it. Why can we not simply build a faster rocket? This is where the physics starts to work against us, and it does so in a way that feels almost personal. Every rocket ever built, from the Saturn V that sent humans to the moon to the ion drives powering some of our deep space probes today, operates on the same principle. You throw mass backward. The equal and opposite reaction pushes you forward. Chemical rockets do it by burning fuel. Ion drives do it by accelerating charged particles. Nuclear thermal engines do it by heating a propellant with a reactor. The physics is identical. Mass goes backward. Ship goes forward. The problem is the fuel. To carry fuel, you need more fuel to move that fuel. To carry that extra fuel, you need more fuel again. The relationship is not linear. It spirals. Think of it like this. Imagine you are trying to lift a ladder out of a well, but the ladder is made of weights, and every rung you pull up makes the ladder heavier, which means you need more rungs, which means more weight, which means more rungs. You can work harder, you can work faster, but the ladder grows faster than you can climb. This is the tyranny of the rocket equation, and it is one of the fundamental reasons why the nearest potentially habitable world, sitting roughly 4 light years away, would take approximately 25,000 years to reach with any propulsion technology we currently have. 25,000 years. At that number, conventional propulsion stops being an engineering problem. It becomes something closer to a prohibition. And the prohibition has a name attached to it. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would eventually place a hard ceiling on everything we have just described. Albert Einstein's theory of special relativity made one claim about motion that changed physics permanently. Nothing with mass, it said, can reach or exceed the speed of light. Not with better fuel, not with better engines, not with any conceivable improvement in technology. The limit is not an engineering barrier, it is a structural rule of reality. Here is why. As an object with mass accelerates toward the speed of light, something strange happens to its mass. It increases. Not linearly, but exponentially. Growing faster and faster the closer the object gets to light speed. The energy required to push it further increases with that mass. More energy means more mass. More mass means more energy required. A spacecraft approaching the speed of light would accumulate so much relativistic mass that to push it further, you would need more energy than exists in the observable universe. At exactly the speed of light, the math resolves to infinity. Not a very large number. Infinity. Particle accelerators have confirmed this in laboratories thousands of times. The Large Hadron Collider at CERN has pushed protons to 99.9991% of the speed of light. At that point, the protons are roughly 7,500 times heavier than they are at rest. The math Einstein wrote in 1905 predicts every measurement with precision. The closer you get to light speed, the heavier you become. The heavier you become, the harder it is to accelerate further. The wall does not just hold firm, it gets thicker the harder you push. But here is where it gets strange. The consequences do not stop at mass. At speeds approaching that of light, time itself begins to behave differently. An astronaut traveling at 99% of the speed of light would experience roughly 10 years of time on board their spacecraft. But back on Earth, somewhere between 70 and 100 years would have passed. They would leave behind a child and return to a world where that child had lived a full life and died of old age. Everyone they knew would be gone. Their departure would feel recent to them. To the Earth, it would be ancient history. This effect, called time dilation, is not theoretical. We measure it continuously in GPS satellites, which must account for relativistic time shifts to maintain accuracy. It is real. There is also length contraction. As an object moves faster, space in the direction of travel appears to compress. Distances seem to shrink. The universe warps around you, not as a metaphor, but as a measurable geometric consequence of moving through space-time at a significant fraction of light speed. The universe does not remain a fixed backdrop. It bends. And then there is causality. If something could travel faster than light, the mathematics allows it to arrive at its destination before it left its origin. Measured from certain reference frames, cause would follow effect. The laws of physics that govern everything we know depend on effects not preceding their causes. Breaking the speed of light would not just break a speed record, it would break the internal logic of the universe, the structure that makes it possible to say that one thing caused another. The universe enforces this the way it enforces the fact that 2 + 2 = 4, not as a preference, as a condition of existence. For generations, physicists taught all of this as settled. Special relativity was foundational. The speed of light was the final word. The prison described at the start of this section was real, permanent, and physically justified. The bars were not made of steel or ignorance. They were made of mathematics. And mathematics had been checked. Most physicists accepted this completely. But a small number, working quietly in the decades that followed, began asking a different kind of question. Not whether Einstein was wrong, but whether the question itself was wrong. Not whether something could move through space faster than light, but whether space itself could be made to move. That question was about to become something more than a thought experiment. Before we follow that question, it helps to sit with just how completely the door has been closed. The energy required to push a single ton of mass to the speed of light is approximately 9 times 10 to the 16th power joules. That number is difficult to hold in the mind, so consider what it represents. It is roughly the total energy output of human civilization for an entire year. Every power plant, every engine, every burning fuel source on the planet, running simultaneously for 12 months, consumed in seconds, for 1 ton. A single small car weighs more than a ton. A crewed spacecraft capable of sustaining human life for an interstellar journey would weigh thousands of times more. The math does not improve with scale. It collapses. Engineers and physicists have not ignored this. They have spent decades searching for a way around it, and the attempts are genuinely impressive. They just fall short. In the 1970s, a group of serious scientists developed a detailed blueprint for an interstellar probe called Project Daedalus. The concept used nuclear fusion rockets, igniting small pellets of deuterium and helium-3 in rapid succession to generate thrust. The design was rigorous, the engineering was real, and the result was a vehicle mostly composed of fuel tanks the size of skyscrapers, carrying 50,000 tons of propellant with a tiny payload at its tip. At full performance, it would reach 12% of the speed of light. That sounds promising until you follow it through. At 12% of light speed, reaching even the outer edges of the nearest star systems would take 2 decades. 2 decades for a probe. Not a crewed mission, not a return trip, a one-way instrument package, and producing 50,000 tons of helium-3 would require harvesting it from the atmosphere of Jupiter. There is no infrastructure for that. There may never be. The speed cap ladder makes the problem vivid. Chemical rockets, the kind that have carried every human being who has ever left Earth, top out around 5 kilometers per second. Ion drives, which use electric fields to accelerate charged particles and are genuinely efficient over long periods, reach 20 to 30 kilometers per second. Nuclear thermal rockets, which heat propellant with a reactor, could push to roughly 50 kilometers per second. Even the most optimistic fusion designs, assuming fueling problems solved, arrive at perhaps 3,000 kilometers per second. That is 1% of light speed. 1%. The gap between that and the nearest star is not a gap that better engineering closes. It is like throwing pebbles at a mountain, hoping to move it. The mountain does not notice. What about antimatter? The physics are elegant. When matter meets antimatter, both convert entirely to energy, 100% conversion, which is the theoretical maximum. No fuel is wasted. Every gram becomes thrust. In principle, an antimatter drive would dwarf anything fusion could achieve. But the reality was different. Antimatter cannot be mined or refined. It must be manufactured, one particle at a time, using enormous particle accelerators. The entire global production of antimatter to date, accumulated across decades of operation at the world's most advanced facilities, amounts to a fraction of a microgram. A microgram, fueling a single interstellar mission at the required scale, would take thousands of years of continuous production, assuming every particle could be captured and stored without annihilating itself, which requires magnetic containment systems drawing enormous power indefinitely. The most efficient fuel imaginable is practically inaccessible. Solar sails offer a different direction entirely. No fuel at all, just an enormous reflective sheet pushed by the pressure of light itself. There is something genuinely beautiful about the concept. Photons carry momentum, and a large enough sail can catch that momentum and accelerate. The Breakthrough Starshot initiative has proposed sails a few meters across, driven by powerful ground-based lasers, potentially reaching 20% of light speed. But the engineering demands are severe. The sail must be miles across to carry anything meaningful. It must be impossibly thin to keep mass low, yet strong enough to survive the journey. Acceleration is measured in tiny fractions per second, building over years and decades. And once you are moving, you cannot stop. There is no braking mechanism. A flyby at 20% of light speed would last seconds at the destination. You would cross the entire Proxima Centauri system in less time than it takes to blink. The conclusion is not that engineers have failed. The conclusion is that the problem is not engineering. The energy trap is structural. It is written into the rules of how mass and motion interact. No refinement of push mass with thrust will cross that gap. A different framework is required. And while we have been examining propulsion, it is worth asking the quieter question underneath. If the stars are unreachable, what about shelter here? What if survival simply meant staying in our own solar system, finding somewhere else to endure if Earth became uninhabitable? Every world in this solar system has been examined with that question in mind. The answers are not encouraging. Mars is the closest candidate. Its distance, its size, its position have made it the default destination in almost every serious discussion of human expansion beyond Earth. But the surface of Mars reaches temperatures of negative 225 degrees Fahrenheit in its coldest regions. The atmosphere is 96% carbon dioxide, and so thin that standing on the Martian surface is the physical equivalent of standing 19 miles above Earth, higher than any aircraft flies, higher than weather exists. Blood would begin to boil in that pressure without a suit. Planet-wide dust storms periodically engulf the entire world for months. And Mars lost its magnetic field billions of years ago, which means its surface is bathed in solar radiation with no natural shielding. Nothing on Mars protects a human being. Everything about it requires constant, total technological intervention just to remain alive. Venus looks closer on a map. It is nearly Earth's twin in size, but the surface temperature is 860 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is equivalent to being 3,000 feet underwater in Earth's oceans. The clouds are made of sulfuric acid. Soviet probes reached the Venusian surface in the 1970s and 1980s, and the most durable of them survived less than 2 hours before being crushed and cooked. Venus is not a candidate. It is a demonstration of how hostile a planet can be while still technically orbiting in the inner solar system. The gas giants offer nothing solid to stand on. Jupiter, Saturn, Uranus, and Neptune are enormous spheres of hydrogen and helium, with pressures that increase catastrophically as you descend and winds that reach 1,000 miles per hour. Their moons are more interesting. Titan, orbiting Saturn, has a thick atmosphere and liquid lakes on its surface. But the liquid is methane. The temperature is negative 290 degrees Fahrenheit. Europa, orbiting Jupiter, may have a liquid water ocean beneath miles of solid ice, possibly vast, possibly warm near hydrothermal vents. But reaching the ocean requires drilling through kilometers of ice in one of the most intensely radiation-saturated environments in the solar system. Mercury offers nothing. Its day side bakes at 800 degrees Fahrenheit. Its night side plunges to negative 300. It has no atmosphere, no water, no magnetic field, no future for anything alive. Terraforming Mars is discussed seriously in some circles, and the ideas are not purely fictional, but the optimistic estimates span thousands of years. They require technologies not yet invented, planetary engineering at scales that dwarf anything humanity has ever attempted, and a continuous commitment across timescales longer than any civilization has ever maintained. Earth is not a temporary home that humanity will eventually outgrow. It is the only viable home we have, possibly for millions of years, and its vulnerabilities are our vulnerabilities. That recognition sits differently once you have looked at what the telescopes have found. There are now more than 5,000 confirmed planets, orbiting other stars. Dozens of them sit in the habitable zones of their stars, the orbital band where liquid water could exist on a surface. Some of them are not just candidates. They are detailed, characterized, observed. Proxima Centauri b orbits the closest star to our Sun at a distance of 4.2 light-years. It sits in the habitable zone. It may have oceans. It may have a magnetic field. It receives energy levels comparable to what Earth receives. In 2017, astronomers announced the TRAPPIST-1 system, 39 light-years away, a small cool star orbited by 7 Earth-sized worlds. 3 of them sit in the habitable zone, stable climates, possible liquid water, possible weather. Possible atmospheres being probed right now by the James Webb Space Telescope, which can detect the signatures of water vapor and oxygen in the light that passes through a distant atmosphere. These are not hypotheticals, these are observations. And then the travel times. Proxima Centauri b, the closest, at current spacecraft speeds, 40,000 years. TRAPPIST-1 at 39 light-years, 600,000 years. Kepler 452b, an Earth-like world orbiting a Sun-like star, 1,400 light-years away, receiving 10% more energy than Earth does. Described as Earth's cousin in nearly every meaningful parameter. 25 million years. Not decades, not centuries. Geological epochs. Timescales longer than our species has existed. The James Webb Telescope can read the chemistry of an atmosphere 40 light-years away. A radio signal sent to Proxima Centauri b would take 4.2 years to arrive. A reply would take 4.2 years to return. Even conversation across the smallest gap spans human generations. We can describe these worlds in extraordinary detail. We know what their air might be made of. We can estimate whether rain falls on their surfaces. We just cannot go there. Not with anything we know how to build. There is a frustration in that which is difficult to sit with calmly. The universe has not hidden these places. It has put them where we can see them perfectly, in fine detail, and simply made the distance a wall that no amount of fuel or thrust or engineering will breach on any timescale that matters to a living thing. Unless, as that quiet question from moments ago still waits to be answered, we stop trying to move through space entirely, and start moving space itself. It was 1994, and the answer came from a graduate student. His name was Miguel Alcubierre. He was working on his doctorate. He had grown up watching science fiction, and one day he sat down with the equations of general relativity and asked a question that almost no one had thought to ask seriously. Not whether matter could be pushed faster than light. That door was closed, but whether space itself could be moved. What he found startled him. The equation said yes, not as speculation, not as a thought experiment, as a mathematically valid configuration derivable from general relativity's own framework, the same framework that had stood unchallenged for nearly 80 years. He published the paper in 1994 in a peer-reviewed journal. The math was checked. It held. Here is the mechanism. Instead of accelerating a ship through space, you build a bubble around the ship. You contract space in front of the bubble and expand space behind it. The asymmetry generates a wave, and the bubble rides that wave forward. The ship inside does nothing. It simply sits there, stationary relative to the local space immediately surrounding it. The wave does the traveling. The ship is a surfer standing still on a board while the ocean itself moves beneath. That distinction is everything. Einstein's limit applies to objects moving through space. It says nothing about space moving. And here is where you realize the loophole was always there, hiding in plain sight. Space moves faster than light right now. It has been doing so for billions of years. The universe expanded from a single point to its current size in roughly 14 billion years. At the edges of the observable universe, space is receding from us faster than light can cross the gap. Not because anything is breaking the rules, but because the rules only govern matter moving through space, not space moving itself. Alcubierre's drive exploits exactly that distinction. Inside the bubble, the physics is ordinary. There is no acceleration pressing you against a wall. There is no time dilation distorting your experience. A journey that takes a week inside the bubble takes a week. You age normally. You pour a cup of coffee and it falls the way coffee falls. The bubble can theoretically reach any speed, 10 times the speed of light, 100 times, 1,000 times, and none of it touches the passenger inside. The energy requirements are astronomical, but they are finite, not infinite, finite. That alone represents an enormous shift from conventional propulsion, which demands literally infinite energy to push matter to light speed. Alcubierre's drive demands a very large finite amount. That is a completely different category of problem. Alcubierre himself said he never expected it to work. He was a student playing with equations inspired by a television program, and the math handed him what looked like a cheat code embedded in the universe's own structure. But to understand why that cheat code works, you have to stop thinking of space as empty nothingness, and start thinking of it as a fabric. This is Einstein's intuition, the one that replaced Newton's vision of space as a fixed, neutral stage. Space and time together form a single continuous medium, space-time, and that medium can bend. It can stretch. It can twist. It can carry ripples. Mass creates dents in this fabric, and those dents are what we experience as gravity. A bowling ball placed on a stretched rubber sheet sinks into a depression, and anything nearby rolls toward it. That is not a perfect analogy, but it captures the essential geometry. This is not philosophy. The evidence is everywhere. GPS satellites orbit high above Earth's surface, where gravity is slightly weaker and time flows measurably faster than at sea level. If the satellites did not account for this difference, every GPS device on Earth would drift by miles within a single day. Atomic clocks carried aboard airplanes returned slightly desynchronized from identical clocks that stayed on the ground. Black holes warp the fabric so severely that even light, moving at the maximum speed the universe permits, cannot climb back out once it crosses the event horizon. The fabric is real, and it behaves. The Alcubierre drive artificially recreates this fabric distortion in an asymmetric pattern around the ship. Contract space ahead, expand space behind. The contraction creates a region where distances compress, pulling the destination closer in geometric terms. The expansion behind pushes the origin away. The bubble surfs the gradient between them. If you were standing outside and watching this happen, the view would be strange. Light from the compressed region ahead cannot easily escape the distortion. The front of the bubble goes partially dark. Light from behind gets stretched into longer wavelengths, redshifting toward radio frequencies, making the rear of the bubble nearly invisible in visible light. The bubble might leave a faint, exotic radiation wake as it passes through the quantum structure of space-time. From inside, looking forward, stars appear closer and shifted toward the blue end of the spectrum. Looking backward, space appears to stretch toward infinity, the light of home pulled into longer and longer wavelengths until it fades. But here is where it gets strange. To warp space-time asymmetrically, the drive requires matter with negative mass and negative energy density, not antimatter. Antimatter has positive mass and annihilates on contact with normal matter in a burst of energy. This is something different. Exotic matter, as physicists call it, would not fall toward other mass. It would fall away from it, where normal matter curves space-time inward, creating gravitational wells. Exotic matter would curve space-time outward, creating gravitational hills. Normal matter attracts, exotic matter repels, in a gravitational sense, at the most fundamental geometric level. It has never been observed. It has never been measured. It has never been created in any laboratory. It exists, so far, only in the mathematics that requires it. And the original Alcubierre design did not require a small amount. It required negative mass equivalent to the total mass energy of Jupiter. Jupiter is roughly 300 times the mass of Earth. To warp space around a small spacecraft, you would need to somehow manufacture or locate that quantity of material that has never been shown to exist anywhere in the universe. The reception among physicists was consistent. The math is valid. The concept is coherent. The material's requirement makes it useless. Critics put it plainly. Asking for Jupiter-mass quantities of a substance that might not exist anywhere in the observable universe is comparable to designing a perpetual motion machine, and then noting that it only requires unicorn tears to run. That verdict held for several years. A brilliant idea with nothing to feed it. Then came a small and stubborn experimental result. 2 uncharged metal plates, placed extremely close together in a vacuum, measuring the quantum energy in the space between them. That space turned out to have measurably less energy than the vacuum surrounding the plates. Not zero, less than zero relative to the surrounding environment, which is the operative definition of negative relative energy density. The effect is called the Casimir effect, and it is real. It has been measured repeatedly in laboratories. It is small. It is not Jupiter mass anything. But it exists. Not theoretical, not inferred, measured. And that changed the question. Not whether negative energy density could exist. It already did. The question became whether an effect that size could ever be scaled to anything useful. That question was nowhere near answered. But the door that critics had treated as locked had turned out to have a crack in it. One small crack. That was all it was. The Casimir effect proved that negative energy density existed in nature, but it did so at scales so tiny, the effect was essentially invisible to anything larger than a few atoms. The question was whether that crack could be widened. And in a building at NASA's Johnson Space Center in Houston, someone had decided to spend years trying. The building is called Building 9. It houses, among other things, full-scale mock-ups of the International Space Station and equipment used to train astronauts for spacewalks. It is not the kind of place most people associate with theoretical physics, but inside it, Dr. Harold White had been running what NASA quietly categorized as future propulsion studies. That label carried enough institutional cover to keep the work alive. What the work actually was, at its core, was an attempt to make warp drive physics something more than a thought experiment. In 2011, White published a set of calculations that shifted the terms of the conversation. The original Alcubierre model had assumed a spherical warp bubble with walls of constant thickness. White asked what would happen if you changed the shape. Reshape the bubble into a torus, a configuration closer to a donut than a sphere, and make the bubble wall oscillate in thickness rather than holding steady. The math changed dramatically. The energy requirement, which had been Jupiter scale in the original design, dropped by multiple orders of magnitude. Not a small refinement, not 10%. The result came down to roughly several hundred kilograms of exotic matter equivalent. Still a staggering quantity. Still far beyond anything humanity has ever produced or measured. But the category of the problem changed. Jupiter mass quantities of an impossible substance made the concept a curiosity at best. Several hundred kilograms made it an engineering challenge. Those are not the same thing. The drive moved from physically impossible to extraordinarily difficult, and that is a genuine distance traveled. What came next was quieter, and it deserves to be treated quietly. In 2021, White's team was running experiments with specialized equipment originally developed for spacecraft attitude control research. The instruments were built to measure nanoscale forces, the kind produced by Casimir effect configurations, with extremely fine sensitivity, while investigating a particular arrangement of capacitor plates designed to create specific local variations in vacuum energy. The instruments registered something unexpected. The readings matched the theoretical signature of a microscopic warp geometry. Not approximately, not roughly. The pattern matched what the equations predicted a miniature warp bubble would look like. The team ran the experiment again and again. The result was consistent. That is the claim, stated plainly. A NASA laboratory detected what appeared to be warp geometry at nanometer scale. Real instruments, repeated measurements, consistent data. Here is also what that claim is not. It has not been independently reproduced. The equipment required is specialized and expensive. Other laboratories have not yet published confirming results. Critics raised reasonable objections. Electromagnetic interference was one. Misinterpreted quantum effects was another. White's team documented their calibration procedures carefully, and the data they produced has not been definitively discredited. But not discredited and confirmed are very different things. The honest position is that the result is strong, interesting, and unconfirmed. It points in a direction. It does not close a question. What it did do, institutionally, was change something. NASA reportedly increased funding to the propulsion research program. Other agencies began paying closer attention. Private aerospace companies started hiring physicists with backgrounds in exotic propulsion. The conversation inside research communities shifted, not dramatically but perceptibly. The question before 2021 was whether warp geometry was purely theoretical. The question after was whether the nanometer scale effect could be scaled up. And that scaling question is the one that puts everything in perspective. The gap between a nanometer scale warp geometry and a meter scale one is roughly a factor of 1 billion, not a factor of 10, not a factor of 1,000, 1 billion. That gap is not a detail. It is the central obstacle. Every subsequent line of research in this field runs directly into it. The mechanism White was exploiting to create those local vacuum variations goes back to what the Casimir effect actually is. Empty space, in the picture quantum field theory gives us, is not empty. It churns constantly with virtual particles, pairs of particles that pop into existence together, borrow their energy briefly from quantum uncertainty, and vanish again before the universe, in a sense, has time to notice. The borrowing and repayment happens on timescales so short they are difficult to express in ordinary terms. But the virtual particles are real while they exist, and they produce a background energy that permeates all of space uniformly. Uniformly under normal conditions. In 1948, Dutch physicist Hendrik Casimir made a prediction. Place two uncharged metal plates close enough together in a vacuum, and the geometry of the gap does something specific to the virtual particles between them. It restricts which wavelengths of virtual particle activity can exist in that confined space. Only wavelengths smaller than the gap fit inside it. Outside the plates, all wavelengths contribute freely. Inside, only the shorter ones do. The result is an imbalance. More quantum pressure pushes the plates together from outside than pushes them apart from inside. The plates move toward each other. There is a measurable attractive force with nothing to produce it except the geometry of the vacuum. That prediction was confirmed experimentally. It has been confirmed many times since. The region between those plates has less quantum vacuum energy than the space surrounding them. Less than the baseline. Negative energy density relative to its environment. Not because something was removed, because the geometry of the space restricted what could exist there. The Casimir effect is, in that precise sense, the first proof that negative energy density occurs in nature, not in a hypothetical, not in an equation written on a board, in a laboratory between two metal plates with instruments to measure it. But something was wrong. The Casimir force is extraordinarily sensitive to distance. Bring the plates together by a factor of 2 and the force changes sharply. Separate them slightly past the threshold where the effect operates and it vanishes. The mechanism that produces the one physical foothold warp drive physics has on reality is also one of the most fragile phenomena in experimental science. Researchers exploring amplification routes have proposed metamaterials, artificially structured materials engineered to interact with electromagnetic fields in ways natural materials cannot, as a possible means of strengthening and stabilizing Casimir-like effects at larger scales. Others have suggested that techniques developed in quantum computing, which require extremely precise control over quantum states, might eventually allow for controlled manipulation of vacuum energy configurations. There is even speculation, unconfirmed, that dark energy, the diffuse pressure pushing the universe's expansion to accelerate, might be related to vacuum energy states that are, in principle, manipulable. All of these remain speculative. The scaling problem has not been solved. Even with White's geometric optimizations, the energy gradients required across a working warp bubble boundary would dwarf anything current technology could sustain. And while the scaling problem remains open, the theoretical landscape around it has been changing. Alcubierre's original design is no longer the only geometry being explored. In 2002, Brazilian physicist José Natario published an alternative model. His formulation used a different tensor field configuration, a different mathematical description of how the space-time distortion would be arranged. Alcubierre's design creates sharp discontinuities at the bubble boundary. The transition from compressed space ahead to normal space inside to expanded space behind happens abruptly, like a cliff edge. That sharpness demands intense local energy concentrations at the boundary itself, and it may also produce Hawking radiation-like effects at the bubble wall, a radiation pattern that could be hazardous to anything nearby. Natario's geometry distributes the distortion across a larger volume. The transition is gradual, a slope instead of a cliff. The peak energy density at any single point drops. The problematic boundary effects may be reduced. His design is harder to describe intuitively, and the mathematics is, if anything, more demanding than Alcubierre's, but it addresses real problems in the original model. Researchers have begun exploring hybrid configurations that combine Natario's smooth boundaries with Alcubierre's oscillating bubble walls, attempting to capture the energy savings of geometric optimization and the stability improvements of smoother transitions simultaneously. A team at the University of Göttingen in Germany has taken the design space further, investigating topologically different geometries entirely. Helical warp fields, braided space-time structures that depart from both Alcubierre and Natario in their fundamental architecture. None of these exists beyond mathematics. No centimeter-scale version of any warp geometry has been built. What has changed is the character of the field. 15 years ago, warp drive was a single theoretical proposal with a single fatal flaw. Now it is a design space. Multiple geometries, each with different trade-offs between energy concentration, boundary stability, and engineering approach, are being studied and compared. The way aeronautics developed different aircraft shapes for different flight regimes, transonic versus supersonic versus subsonic. The way each design solved different problems while sharing the same underlying physics. Something similar is beginning to emerge here. Competing proposals are not a sign of confusion. They are a sign of a field maturing. What none of them have yet resolved is whether any warp geometry can be realized at scales large enough to matter. And the worry about Hawking-like radiation at the bubble boundary, radiation that could endanger anything in its vicinity, is not settled by any of the current designs. The geometry problem and the energy problem and the radiation problem have each been worked on separately. Whether they can all be solved together in a single design is a question the field has not yet faced squarely. And if that disturbance is real, it might not only be ours we can listen for. Gravitational waves are ripples in space-time. When massive objects accelerate violently, colliding black holes, merging neutron stars, the cores of collapsing stars, the fabric of space itself shudders outward from the event at the speed of light. The waves are extraordinarily faint by the time they reach us. LIGO and Virgo, the gravitational wave observatories, measure distortions smaller than a proton's diameter. Not smaller than a human hair. Not smaller than a cell. Smaller than a proton. That is the threshold of sensitivity humanity has achieved. And in 2015 it paid off. The first confirmed detection of gravitational waves arrived at the detectors as a chirp lasting less than a second. Two black holes had merged more than 1 billion light years away, and the shudder of that merger reached Earth as a tremor that moved the detector's mirrors by a distance too small to see and too significant to ignore. Now consider what a warp drive would do to space-time. A warp bubble is by its nature a violent and deliberate distortion of space-time geometry. It contracts space in one direction and expands it in another. That is not a passive process. It is an active rearrangement of the fabric that gravitational wave observatories are designed to hear. In 2024, a team at Germany's University of Potsdam published a formal proposal. They simulated the gravitational wave signatures expected from different warp drive designs. They calculated frequencies, amplitudes, and polarization patterns. Then they did something bolder. They went back through the existing gravitational wave archives, the accumulated data from every detection run LIGO and Virgo had completed, and searched for matches. They found none. But that finding is not a closed door. Gravitational wave astronomy is still young. The detectors of the coming decade will be substantially more sensitive than the ones that first heard black holes collide. And if any civilization within the observable universe is using warp drives right now, those ripples are already traveling toward us at the speed of light. We may not have the instruments to hear them yet. That does not mean they are not coming. Think about what a confirmed detection would mean. Not a radio signal, not a mathematical pattern in a background survey, a gravitational wave signature carrying the geometry of a warp bubble. That single detection would answer two of the largest questions in the history of science simultaneously. It would confirm that we are not alone, and it would confirm that faster than light travel is physically possible. Not speculative, not theoretically permitted, demonstrated by someone, somewhere. It would also give us a working model to study. We could measure the bubble's geometry from the wave's shape. We could infer energy distributions from its amplitude. We could estimate the drive's operating cycle from how the signature changes over time. The ship itself would be unreachable, but its physics would be readable. There is a historical precedent for this kind of reconstruction. The Antikythera mechanism, a Greek astronomical calculator built around 150 BC, was pulled from a shipwreck in fragments. No drawings existed. No manual survived. Modern analysis eventually decoded it anyway, layer by layer, working from the object's own internal logic. Advanced technology, even when you cannot ask its makers how it works, carries its design in its behavior. There are caveats. An advanced civilization operating warp drives might have addressed the signature problem long ago. They might modify their bubble geometry specifically to minimize detectable emissions. They might avoid the populated regions of the galaxy. They might have achieved a kind of technological silence we have not thought to look for. And there is a harder question beneath that one. If an alien civilization went to the trouble of suppressing its warp signatures, should we be trying to decode the ones that slipped through? There is an ethical weight to reverse engineering technology that someone chose to hide. We do not know why they hid it. We do not know what they knew about its effects that we do not. If the signatures reveal that warp drives carry hazardous side effects, that might explain precisely why advanced civilizations use them sparingly. The silence of the sky has always raised uncomfortable questions. This search adds a new one. But if FTL is real, the deepest worry isn't whether we can detect it from across the galaxy. It is something closer to home, something that lives inside the physics itself. The worry is causality. Warp travel that moves faster than light could, in principle, enable an observer in a different reference frame to watch you arrive before you left. That is not a riddle. That is how the geometry works. And from there, the logic spirals. If you can arrive before you left, you can communicate information backwards through time. If you can communicate backwards through time, you can in principle prevent the conditions that caused your departure. The grandfather paradox is the compact version. Travel back, prevent your grandparents from meeting. You are never born, you never travel. They do meet. You are born, you travel. The loop has no consistent solution. Some physicists argue this proves FTL must be impossible. Not difficult, not dangerous, impossible, because the universe does not permit paradoxes. Stephen Hawking called this the chronology protection conjecture. The idea is that unknown physics intervenes whenever a closed loop would otherwise form. The universe enforces the no paradox rule, even if we cannot yet write down the mechanism. But there is a counter-argument, and it is specific to warp drives. Nothing inside a warp bubble crosses the local speed of light. The bubble is not a loophole in special relativity. It is an exploitation of general relativity's flexibility at larger scales. More importantly, the bubble's interior is isolated from external reference frames. Information cannot propagate back through the bubble boundary. You cannot use the bubble to send a signal to your own past because the geometry of the boundary prevents it, and the energy supply is strictly real-time. You cannot retroactively fuel a bubble that has already collapsed. The conditions for a paradox require that information flow back through the same path it traveled forward, and the bubble's own structure may block that path in a way that is not merely engineering, but geometric. The loophole might close itself. There is also the many worlds escape. In one interpretation of a quantum mechanics, every branching event generates a new timeline rather than altering the existing one. Under that framework, backward travel doesn't create a paradox. It creates a branch. The original timeline continues unchanged. The grandfather you prevented from meeting your grandmother in the new branch was never the grandfather of the person who traveled. The contradiction dissolves. It does so at a considerable cost, an infinite proliferation of parallel realities, but the internal logic holds. We don't know which interpretation of quantum mechanics is correct. We don't know whether many worlds is the right framework. What we know is that warp drives, if they avoid paradoxes, may avoid them not by luck, but by the structure of their own geometry. And then the physics offers something unexpected. A gift, almost. Consider the alternative. A ship accelerating to a significant fraction of light speed using conventional propulsion faces a brutal trade-off. At 99% of light speed, roughly 10 years on board becomes 70 years on Earth. The travelers return younger than the people they left. Loved ones have aged or died. The civilization that funded the mission has moved on. It is not a speculation. Particle accelerators confirm it. Unstable particles at 99% of light speed decay measurably slower than the same particles at rest. The effect is real and has been measured thousands of times. Generation ships avoid this by traveling slowly over centuries, but that introduces its own costs. Social drift, mission continuity across generations, cultural change over timescales no institution has managed before. A warp bubble sidesteps the problem entirely. The ship inside is not moving through space at relativistic speed. Space is moving around it. The ship's clocks run at normal rates. You leave, you travel, you return, and the time elapsed on the ship matches the time elapsed at home. Journey to Proxima Centauri in weeks. Return to find weeks have passed. That makes interstellar work economically coherent. Investment with a return horizon of decades, not centuries. And there is still one more advantage, the one that doesn't get discussed as often. Accelerating a human body to a meaningful fraction of light speed, even gradually, requires enormous sustained force. Astronauts endure roughly 3 times Earth's gravity during launch. Fighter pilots can withstand around 9 times Earth's gravity briefly, before losing consciousness. Getting to a meaningful fraction of light speed in any reasonable time frame would require forces thousands of times that, fatal in seconds. Generation ships avoid this by accelerating over decades, trading crushing force for glacial pace. Cryogenic suspension doesn't solve it either. Ice crystals form during the freezing process and shred cells from within. It remains science fiction. Inside a warp bubble, none of this applies. The bubble does not push the ship. It carries it. There is no acceleration in the conventional sense. No inertial force presses against the crew. No G-load, no pressure on the walls, no sensation of motion. The transition from rest to multiples of light speed is imperceptible from inside. You are, in the most literal sense, standing still while the universe rearranges itself around you. Fragile equipment travels unharmed. Living organisms arrive without trauma. Volatile chemicals remain stable. Entire ecosystems, if someone chose to transport them, could travel intact. The engineering problems of hardening a spacecraft against its own acceleration, problems that constrain every conventional design from the first rocket equation to the most optimistic fusion concept, vanish. Not reduced, not mitigated. Removed from the problem space entirely. Even if warp drives were only marginally faster than conventional propulsion, that alone would change the calculus of space travel in ways that are difficult to fully trace. But that question, what warp travel would actually mean for everything it carried and everyone it returned, depends first on whether it can be built. And that depends on whether the physics holds together at scales beyond a nanometer, at energies beyond a laboratory, in a bubble large enough for something to live inside. That is the question the field has been circling. And it is not the only one left. Let's stay inside that bubble a moment longer. From where you're sitting, nothing unusual is happening. Air moves normally. A watch ticks. A candle flame, if someone brought one, would burn at the same rate it always has. Light inside the bubble travels at the speed of light, as it always does, relative to the space around you. The physics you grew up inside is intact. You cannot feel velocity. You cannot measure it with any instrument aboard. Whether the bubble is carrying you at 10 times the speed of light or sitting perfectly still, the experience from inside is identical. The universe outside is reorganizing itself around you, and you simply cannot tell. What you could see through a forward window, if you had one, is another matter. Space ahead is being compressed. The light from stars in that direction is being squeezed to shorter and shorter wavelengths. Blue shifting out of the visible spectrum and into the ultraviolet, then the X-ray, then the gamma-ray range. There would be nothing recognizable there to see. Behind you, the opposite is happening. Rear-facing stars shift into the radio spectrum, invisible to the eye. The visible light that remains compresses into a ring around your field of view, a narrow band at roughly 90 degrees from your direction of travel. The only portion of space where wavelengths still fall in the range, human eyes register. Some models suggest there would be no forward view at all, an effect not unlike the way a black hole's event horizon cuts off the light coming from behind it. Navigation would be entirely by instrument, and yet the bubble itself is protective. Cosmic microwave background radiation, the faint afterglow of the early universe that permeates all of space, cannot easily penetrate the boundary. Interstellar dust, which would ablate the hull of any conventional spacecraft at a significant fraction of light speed, is deflected. The extreme curvature of the bubble's boundary acts as a kind of shield. Theoretically, you could warp through a region of intense stellar radiation without the interior registering it. Some calculations suggest you could pass through the edge of a supernova's shockwave and feel nothing. Not reduced exposure, not better shielding, nothing. Communication is a different problem. Radio signals cannot easily cross the bubble boundary's extreme curvature. A ship in warp is, for practical purposes, cut off. There is no signal that reaches home, and no signal from home that reaches the ship. A transit of days or weeks, depending on the distance covered, would pass in effective silence. Mission planners would need to account for this by placing full information and full decision authority aboard the ship before departure. The crew would navigate, decide, and if anything went wrong, respond without consultation. The psychological weight of that isolation, being inside an island of calm, ordinary reality while the cosmos restructures itself outside and every other human being is temporarily unreachable, would be something no previous space mission has asked of its crew. Training would need to emphasize routine, familiarity, the ordinariness of the interior as an anchor against the strangeness of the exterior. It would still be vastly preferable by any measure to a generation ship spanning decades. Now, think about who is actually working on this. NASA's Advanced Propulsion Physics Laboratory at Johnson Space Center continued to operate after the 2021 result, with research tracks running simultaneously across the Casimir effect, metamaterials for vacuum manipulation, and the relationship between quantum entanglement and spacetime geometry. Glenn Research Center in Ohio contributes propulsion expertise. The Jet Propulsion Laboratory handles engineering analysis. Ames Research Center runs computational modeling. These are not informal efforts. They are funded, staffed, and ongoing. The Department of Energy is almost certainly involved, though not visibly. The energy requirements for any working warp configuration overlap directly with the department's existing expertise in plasma physics, high-energy particle interactions, and the national laboratory system that stretches from Oak Ridge to Sandia to Lawrence Livermore. The fusion researchers, the plasma physicists, the particle accelerator engineers are already working on problems that feed directly into warp-relevant physics. Whether those connections are formalized is not public, and some of this is almost certainly classified. Warp drive is not primarily a scientific curiosity to a defense agency. It is a strategic technology of the highest order. A civilization that achieves it first does not simply win a race to the stars. The patterns that have appeared in recent years, the conference presentations with oddly vague language around spacetime manipulation, the unexplained anomalies mentioned in passing and then not followed up in public literature, these are not accidents. In the private sector, the picture is less opaque but still incomplete. SpaceX has never publicly announced a warp research program. What it has done is post hiring notices for plasma physicists, quantum field theorists, and engineers with general relativity backgrounds for, as the postings describe it, unspecified advanced projects. Blue Origin, Lockheed Martin, Boeing, and Northrop Grumman all maintain advanced concepts divisions. None of them discuss this openly. Yuri Milner's Breakthrough Initiatives funds related work at the edge of known propulsion physics. Breakthrough Starshot, the project that proposes laser-propelled probes at 20% of the speed of light toward Alpha Centauri, has already demonstrated that private capital can move faster than institutional inertia on propulsion questions. By 2026, 3 distinct theoretical approaches are being seriously pursued. The first is the optimized Alcubierre bubble, which we have covered in detail, focused on using cascading Casimir resonance to amplify small vacuum energy effects, the way an opera singer can shatter a wine glass not by brute force, but by finding the resonant frequency that lets a small sustained input produce a large structural result. The second is Natario-style smooth field distributions, which spread the space-time distortion gradually rather than sharply, and which may be achievable through toroidal plasma containment arrangements that draw on fusion-style engineering. The gradual boundary reduces the hazardous radiation effects at the bubble's edge, and may require somewhat less exotic energy concentration. The third approach is different in kind from the first two, and it deserves more attention than it typically receives. Dark energy is not a gap in our knowledge waiting to be filled. It is a measured, confirmed component of the universe, constituting roughly 70% of the universe's total energy density. The other 30% is matter, both ordinary and dark, all the galaxies, stars, planets, gas clouds, and dark matter halos that make up everything we can see or infer. Dark energy is the rest, and it has a property that sets it apart from anything else in physics. It exhibits negative pressure. That is not a metaphor. Negative pressure is a precise physical description of something that pulls space apart rather than pushing it together, that causes the expansion of the universe to accelerate rather than slow. It is the property warp drives need, not a property vaguely similar to what warp drives need. Exactly the property expressed in the same mathematical terms. Something else was happening. Dark energy permeates every cubic meter of space, everywhere, without exception. It is not concentrated in special regions. It is not rare. It is not exotic in the sense of being absent from ordinary environments. It is present in the room around you right now, and in the space between galaxies, in equal measure. If it can be tapped, if humanity ever learns to locally concentrate or redirect it, the fuel problem dissolves. Not partially. The universe itself becomes the fuel source, inexhaustible, already present at every point where a warp bubble might form. Humanity may already be swimming in the energy it needs. It simply cannot yet measure it locally, let alone manipulate it. Detecting dark energy at cosmic scales, across billions of light years of accumulated effect, is possible. Detecting its presence in a laboratory, in a single cubic meter, in anything smaller than an enormous cosmological measurement, remains beyond current instrumentation. It is like trying to measure a tiny current while standing in the ocean. The current is real. The ocean is everywhere. And the tools for measuring 1 cubic meter of it precisely do not yet exist. Warp bubble formation may naturally interact with dark energy in useful ways, since altering local space-time geometry changes the conditions under which dark energy behaves. Whether this interaction can be made deliberate is a question that sits at the intersection of general relativity, quantum field theory, and cosmology, and no one currently has the tools to answer it rigorously. The deeper question is more unsettling. Einstein's general relativity describes space-time as a smooth, continuous fabric, seamlessly curved by mass and energy, with no gaps, no grain, no minimum unit. Quantum mechanics describes everything else as fundamentally grainy, built from discrete packets that cannot be subdivided below a certain scale. These two descriptions work brilliantly in their own domains. They fail completely when applied simultaneously. At the Planck length, approximately 10 to the negative 35th meters, the smallest meaningful distance in physics, spacetime's smooth description breaks down. Below that scale, the geometry of space and time as continuous quantities stops making sense. The fabric may be pixelated, the way a digital image looks smooth from a distance, but reveals individual pixels under enough magnification. If that is true, if space-time has a grain to it at that scale, then there may be seams, natural boundaries between adjacent units of space-time where the structure is not seamless, where the geometry transitions from one state to another. Those seams, if they exist, could be the places where manipulation is structurally easier. Not a tailor cutting randomly across a fabric, but cutting along the weave, finding the places where the material is already organized for separation. Black hole event horizons are the most dramatic real-world examples of extreme space-time boundaries, places where the curvature becomes so steep that the interior is causally severed from the exterior. Wormholes, which require the same exotic matter as warp drives, represent a different configuration of the same underlying possibility. Some physicists describe warp bubbles as mobile, self-contained mini wormholes, carrying a pocket of normal space-time. String theory suggests that at extreme curvatures, additional spatial dimensions currently folded below the Planck scale might become accessible. Loop quantum gravity treats space-time as woven from discrete quantum loops, which means, if it is correct, that space-time has component parts and can, in principle, be unwoven and rewoven. Cosmic strings, hypothetical one-dimensional defects from the very early universe, would represent natural large-scale seams, if they exist, and have not yet been detected. None of these are confirmations. All of them point at the same possibility. The universe may have structure that warp drives could exploit, structure that sits beneath the resolution of every instrument currently built. The timeline question forces honesty. Optimists place a working prototype at 10 to 15 years, contingent on a major theoretical breakthrough, followed by aggressive engineering. Pessimists place it at centuries, or consider it permanently impossible. Reality is probably somewhere between those poles, but the gap between them is genuinely wide. What is not wide is the funding. Current warp research worldwide totals in the millions of dollars per year. Fusion energy research, which has been pursued for decades and has not yet achieved sustained net energy gain. Fusion has been 30 years away for more than 60 years now, receives billions per year. The Manhattan Project cost the equivalent of roughly $27 billion in today's money over 4 years and produced nuclear weapons. The Apollo program cost roughly $150 billion in today's money and landed humans on the moon within a decade of Kennedy's announcement. If humanity redirected Apollo-scale resources toward warp research, the 10 to 15 year optimist timeline would not be outlandish. It would be historically plausible. Powered flight went from barely possible to routine in less than 2 decades. Nuclear energy went from theoretical to practical in roughly 5 years once serious resources were committed. The room-sized computer became the pocket-sized one in 30 years. Breakthroughs, when they come, can come fast. The question is whether the universe physically permits the required technologies, and whether humanity chooses to find out. If it does succeed, the stakes are civilizational. Within 50 light-years of Earth, there are hundreds of stellar systems. Several dozen have been identified as potentially interesting for planetary habitability. A warp drive capable of carrying a ship at even a modest multiple of light speed would place all of them within the reach of a human lifetime. Not a generation ship, not a one-way sacrifice. A journey out, and if desired, a journey home. Humanity would become a multi-world species, not as a fantasy, but as a practical condition. The redundancy against Earth-based catastrophe alone, fire, disease, impact, institutional collapse, would change the long-term survival calculation of the species entirely. The economic consequences of access to asteroid fields, rare elements, and stellar energy sources in other systems are too large to model seriously. Contact with alien life, even ruins, even microbial chemistry, becomes a physically plausible event rather than a thought experiment. The psychological consequence may be the most profound. Knowing the stars are reachable changes how a civilization thinks about itself. Not imprisoned, free. The risks are real as well. A technology that moves ships at multiples of light speed is also a weapon delivery system of unprecedented capability. The first nation or entity to acquire it does not simply gain scientific reach. It gains a strategic advantage with no historical analogue. Environmental damage to space-time from repeated warp travel is not something anyone can currently model. The ethical obligations toward any life found in other systems, primitive, complex, or somewhere between, have not been worked out. Access questions, who can go, on whose terms, governed by which frameworks, have not been addressed. These are not afterthoughts. They are problems that need to be solved before the drive exists, not after. Even if everything works, the reach is bounded. The observable universe extends roughly as far as light has traveled in the age of the cosmos, and its outermost edges are receding faster than any ship could follow. Even at 1,000 times the speed of light, crossing the observable universe would take millions of years. The stars are reachable. The whole of the universe is not. The real prize is the local neighborhood, a few dozen nearby systems, a few hundred at ambition's limit, enough to answer the questions that have been waiting since the first person looked up and wondered whether anything else was out there. The laboratories working on this today are quiet places. The experiments involve nanoscale distances, careful measurements, computational simulations running through millions of bubble configurations, the way pharmaceutical research screens molecules. The people doing this work know the gap between what they can demonstrate and what a working drive would require. They know it precisely because they have calculated it. They are not naive about the distance remaining, and they are working anyway. One equation, one experiment, one careful result at a time, on the longest chain of reasoning in the history of human ambition. The future that depends on this work has not been written yet. It is being written now.